Current and potential difference in series and parallel circuits. Here we have a series circuit with a cell at the top and a lamp, and I'll show a charge Q carrying energy E, and the charge travels around the circuit delivering energy to the lamp then lights, the charge continues to pick up more energy and go around the circuit again. So the charge is continuing and the charge delivers energy. The same amount of charge passes this point in the circuit as passes this point and this point. Here we have another circuit with two lamps, and now the charges are picking up 2 units of energy, and you'll see they're delivering 1 unit of energy to the first lamp and the other unit of energy to the second lamp. If the lamps have identical resistances, each will get the same amount of energy. The charge is sharing its energy between this lamp and this lamp. Again, the same amount of charge passes this point in the circuit in a second as this point and this point. So the rate of transfer of charge, or the current, is the same all around the circuit. The energy given to the charge here is shared between the components in the circuit. So the potential difference across the cell is equal to the sum of the potential difference across here and here. Here we have a parallel circuit. Now the charges come out of the battery carrying energy. They again have 2 units of energy, and some of them will go this way, delivering their energy to the top lamp. Some are going this way, delivering their energy to the bottom lamp. The charges have to come back empty, having delivered all their energy. So therefore they're picking up 2 units of energy. If they go this way, they deliver 2 units of energy to this lamp. If they go this way, they deliver 2 units of energy to this lamp. The amount of charge travelling in this part of the circuit in a second is equal to the amount of charge travelling in this part plus the amount of charge travelling in this part. So the charge passing per second, or the current, in the branches adds to give the current in the main part of the circuit. The potential difference, or energy transferred, to the charges across the cell is equal to the potential difference, or the energy transferred from the charges to this lamp and to this lamp. So the potential difference across the cell is the same as the potential difference across each of the branches. So the current entering a junction must equal the current leaving a junction. The number of charges doesn't change. So with a junction here, if we have 2 amps, 2 coulombs passing per second coming into this junction, and if we have 1.5 amps passing up the top branch, there must be 0.5 amps passing along the bottom branch. In all these circuits, we've assumed that ammeters have 0 resistance and that voltmeters have infinite resistance. This isn't quite true in real circuits, but it's a good enough assumption. Here we have a circuit with a cell and a 2 ohm resistor and a 4 ohm resistor. So this resistor has got twice the resistance, is twice as hard to get through as this one. It will therefore require twice the energy. If we have an ammeter here, here and here, the amount of charges passing per second through here must be the same as passing through here and passing through here. The voltmeter here measures the energy delivered to the charges as they pass through the cell. The voltmeter here, the amount of energy transferred to the 2 ohm resistor, and this gives the amount of energy transferred to the 4 ohm resistor. The current is the same all around the series circuit. So therefore the reading of ammeter 1 will equal that of ammeter 2 and of ammeter 3. The potential difference is shared by the components in a series circuit. So voltmeter 1, the energy transferred to the charges by the cell, will equal the sum of voltmeter 2 and voltmeter 3, the energy transferred to the resistors. If voltmeter 1 is equal to 3 volts and voltmeter 2 is equal to 1 volt, then voltmeter 3 must be equal to 2 volts, because 1 plus 2 equals 3. Using Ohm's law for the 2 ohm resistor, we have current as potential difference over resistance, and the potential difference is 1 volt, the resistance 2 ohms, giving a current of half an amp. So the current all around the circuit will be half an amp. Here we have a parallel circuit, and now the voltmeters would give the same reading. The energy given to the charge by the cell is the same as that given to any of the branches. So voltmeter 1 would have the same reading as voltmeter 2 and of voltmeter 3. The potential difference is the same across each branch of a parallel circuit. With the ammeters, the current flowing around here is the same as the sum of the current passing through this branch and this branch. So ammeter 1 here will equal the sum of ammeter 2 and 3, and will be the same as ammeter 4. So we can say that the current is shared between the branches of a parallel circuit. If voltmeter 1 is equal to 3 volts, then voltmeter 2 and voltmeter 3 will also be equal to 3 volts. Using Ohm's law for the 2 ohm resistor, we have current is potential difference over resistance, which is 3 volts over 2 ohms, giving a current of 1.5 amps through the 2 ohm resistor. Using Ohm's law for the 4 ohm resistor, we have I is V over R, which is now 3 over 4, which is 0.75 amps. It's also worth noting that this bottom branch, 4 ohms, is twice as difficult to get through as 2 ohms, and so this branch is carrying half the current. 0.75 amps is half of the 1.5 amps travelling through this branch. The lower branch has twice the resistance and half the current.